Okay. All right. So I just quickly mentioned that UNSW, on behalf of my colleagues from UNSW, I want to thank our colleagues from ISC for this joint workshop. So greetings from UNSW. We are a top 20 global university. Uh, I also represent UNSW AI Institute, so I thought I'd bring this up. It's an institute that's pan-university across all faculty at UNSW. We do all things related to AI. So here's my talk about multimodal sensing and AI for individual and public health monitoring. So my research group is called CRUISE, Collaborative Human-Centric AI Systems. And we basically working on in the intersection of AI machine learning with ubiquitous computing. Ubiquitous includes mobile and wearable and multimodal sensing in the wild. So what we've been working on very much is looking at think about scenarios where you have people wearing all kind of sensors, and how do we build accurate behavioral profiles that can then be used to can be used as a predictive model for anything related to health monitoring and other utilities as well. And if you think about this, and doing it in a privacy preserving manner as well, we can then actually scale it up and bring it at basic community level. So then a lot of the work that we've been doing is looking at not just these sensors across individuals, but also sensors across population and across the city, and that the whole problem space that we're looking at are very much about machine learning with time series and spatial temporal data. So if you think about spatial temporal data, that's basically any data that is associated with location and time and axis attribute. So that can be event data, trajectory, raster, and many things else. So going back to the aspect of multimodal sensing, continuous learning, we've been looking at all kind of different problems. For example, one area, for example, could be profiling human personality or with mobile sensing, looking at behavior, emotion, cognition sensing using multimodal sensors. This is done closely in collaboration with my colleague Benjamin Tack. We have several students together on this topic. For example, think about people having no longer just smart watches to keep their activity tracking for step counting and sleep monitoring and all that. But now these days we also have wearable glasses, and people will need help to be able to interact with the environment and get information on their fingertips right away. So with all these challenges, the work that we do are very much looking at foundational AI for multimodal time series. And with time series in the wild, there's a lot of challenges: missing data, irregularity, heterogeneous data. We always work with off-the-shelf sensors, so all kind of sensors, and we have no assumption about those sensors. So and distribution can change. So we came up with different methods with this. For example, so some of these classes methods, self-supervised learning, and many things. And in fact, a lot of sensor data we deal with that they don't have annotation is very much easier to get labeled data from images on the left, but not sensors on the right. Especially if we work on anomalous behavior. If let's say some of our users might have cardiac arrhythmia, right? And we have ECG that's coming from sensor in the wild, actually, not those actually from the hospital clinical readings. How do you actually distinguish these things? And a lot of times you need reliable, potentially feature engineering methods, but we do not want to use handcrafted features because there's too many of them if we work with all kind of data. So we've been very much working on self-supervised learning framework that can actually learn cross-modality augmentation across different sensors. And how do you actually then build, for example, self-supervised representation that will be robust regardless of the task. For example, here with cocoa paper, we have tested the self-supervised learning method, and it works without labeled data for different tasks: human active recognition, sleep stage detection, emotion recognition, and many more. And even with only 10% of labels, we can outperform fully supervised baselines. So some of the work that we've done is, well, we're the first who did federated on-edge learning that is completely self-supervised, so do not rely on labeled data. So this was published in an Internet of Things journal, which means you can actually learn individual sensor representation of behavior of individual users, for example, here, and you don't know, for example, you don't know what the label are of this EEG. We just build an augmentation. For example, here we use a wavelet transformation module, and we can have a very strong representation about that. And although we may not know what these behavior are, in here, for example, if you look at the TSNE map, some of these classes represent wakefulness or REM sleep and all those things. So with a bit of label that we know what these classes are. So this can be built on the edge, and then the federated model will be able to optimize it across all the edge devices. So this is what is also interesting with our model. You even just need 10% up to just 10% to be equivalent to fully trained supervised learning model that's typically required. So we have also built models that can be robust. So self-supervised learning method that can be robust to missing data or missing channel at pre-training or fine-tuning stage or inference time. This method is now already adopted by Nokia Bell Labs, patented by them as well, and adopted in their platform. They have been building things like earables. So the earables will have dependency potentially with mobile data and other things if people do not always wear the earpods. And earables now these days, they have other things. They have PPG sensors, they have EEG sensors, and many things, not just IMU. So the next level of sensing will be done on the ear. We also have been working with audio signals, such as cough, for example, here. In fact, we've been utilizing Sriram's dataset for this. Thank you, Sri, for sharing the dataset. So our work in KDD 2021 was the first self-supervised learning method that did not require any labeled data. We built a contrastive pre-trained model that will be robust to any kind of the cough representations. The details are in the paper. The most recent one was this model called CoughVit, Cough Vision Transformer. So we can actually transform that cough signals into spectrogram reconstruction problem. And also on sleep, we have collaboration with Tsinghua University in combination of, instead of using PPG, we use rings. So rings and earables to be able to detect PPG, motion, SpO2, breath signals, and all that. And being able to detect sleep activity even on individual when they're sharing. So try to detect, for example, someone snore, but not my snore. It cannot be my husband's snore. It has to be my, my condition, not. So this is quite actually a challenging problem if you want to do in the wild sensing at home environment. We also work with irregular time series. So rather than expecting sensor coming data at every regular sampling rate, if data is irregular, we build some, rather than trying to do imputation manually before, can we build an imputation on the latent space? So this is a neural ODE architecture to build imputation on the latent space. And also if the distribution changes, we also build sequence data. Let me just quickly move. I will have to. So we build also on cognition and information processing. We have got a lot of data also on multimodal sensing on this area. And also we're working on the area of public health monitoring. So in this space, public health monitoring, because as I say, we also work with large scale sensor data from, for example, traffic flow and many things. We have been working in collaboration with epidemiologists from UNSW and also George Mason University and Emory as part of this NSF CSRO grant between Australia and US on epidemiology forecasting. So one of the things that we've been working is we have been tracking avian flu across the US. And the problem with that is a lot of these avian flu cases, they are not sequenced. And that means being able to predict outbreaks without ages on this graph are very difficult. So we have been building methods for imputation of spatial temporal pathogen graph, for example. And then now we have a model that actually can then take into account the graph imputation of the phylogenetic combination with migration flow of the bird so that we can actually predict cases at least a couple of weeks ahead of time. So this is the fusion network model that we have. We also have a causal inference network, so we actually can extract the causal factors. And finally, we also been working on LLM alignment with sensors, so we can then do human actor recognition without very expensive dense features. So this is an EMNLP paper, sensor LLM. I'll skip this part. We also have been working on generative AI simulation to be able to look at how we simulate what if scenarios if we have interventions. So that's it from me. Thank you.